Okay, so let's start again. So last week we had this Linköping-driven cavity problem started, and I described the physical situation there. And I also told you that there is a report in which you have details on the main method. And now this subject is pretty tough because it's a huge topic of solving the Navier-Stokes directly using numerical methods and numerical discretization. So basically, in this report, and what I encourage you to do is basically to study it if you want to go deeper and deeper into CFD. Because for you, I have two other tasks to do during this course, but this is a method that you may also like if you know something about numerical methods of solving partial differential equations, because it's pretty straightforward. So basically, what this report covers. So this is a solution to two-dimensional incompressible Navier-Stokes. That's why we work with driven cavity here, with three distinct methods. First is simple, then there is a simpler. Simpler is simple revisited. You remember from last week, I told you simple is semi-implicit method for pressure-linked equations. Simpler is the same revisited, because that's like an extension of the method for transient flows. So for the flows with a time-dependent component of the main equation. And then we have a very interesting vorticity-stream function approach, which I will also tell you something about today, just to give you some perspective on in which direction you may go if you like. Please remember, because that's a specialized lecture, that's why I don't go deeper and deeper into everything. I also want to give you an overview, and this is part of the overview of the methods. So today, we don't think like I will implement this tomorrow evening, but you are welcome to work with it and come to me and ask questions and so on. Anyway, so let's go into simpler and vorticity stream function approach. What is this all about? So I obviously did not invent the methods. I was working with a book of Professor Anderson, so you are welcome to see the book in the course materials. I gave you the link, but it's not the only source. There are more, and those sources that I was using to study those methods are listed in the report. So consider that, because I was given that as a student, and the sources are perfect because they really like give a very proper introduction. So what do we solve? I will just go through the background. We again solve the Navier-Stokes, and this is pretty much the whole course about that, because we are solving the same equation all the time. We reformulate it in the partial differential forms. So all those questions that you write on the paper regarding the symbols that we have in the equation, they are shown here, because you need to know what nabla is. If you know what nabla is, then you can basically rewrite it in the partial differential form, and this is more clear because that's a partial differential equation, continuity equation, and those equations are discretized. So then we can basically write down a code. If you discretize them on a grid, then you can write down then this plus this over delta t or delta x is equal something, yeah? Yes, and the simple algorithm. The problem with Navier-Stokes equations is that if you solve the momentum equation, okay, those two equations here, why do we have two? Because that's two-dimensional. If you had the three dimensions, then you would have the z component of velocity. But the main problem with those equations is that you don't have only those two. I mean, one equation, you have two which have to be fulfilled. So this equation is very often not fulfilled. The continuity is broken when you solve momentum equation. And that's the main source of all the methods, of the whole zoo of methods in CFD. And this is why we need to use some specialized numerical algorithms to solve those equations. And that's pretty much the main problem and issue in this community, because there is no single state-of-the-art method that will work for every fluid and for every situation. And that's why we are like still continuously developing methods and showing some solution. Okay, so again, if you solve this numerically, this will not be fulfilled. And the simple algorithm is a numerical procedure to make the predictor-corrector like steps that helps you to keep the solution going towards the proper solution in which the both momentum and the pressure and the continuity equation is fulfilled. And this is done by linking the velocity fluctuations into the, I mean, the like the errors, because if this term is not equal to 0, that means we are having some errors in the solution. That means there is some kind of discontinuity in the flow. Yeah, the divergence should be 0. That's basically this equation. If this is not 0, that means we need to put something into momentum to make it to smooth it out. And the idea of the simple, which I will not derive here, but there is a book on simple method. I give you the reference in a moment. The idea of creating this algorithm is to link the pressure, which is in the continuity equation, with the velocity by using the errors, so the discontinuity of the flow, as a source term for the pressure. So physically, that means if there is some kind of error, it will be creating forces in the flow. And yeah, so this will be this pressure link for between those two equations. Okay. Okay. And how does it work? So first we have to guess the initial values for the pressure and the velocity fields, and then we solve those two equations 3 and 4. These are the momentum equations. Okay, to get the values on the next time step. How to solve them I will show you in a moment. So first we solve those two equations. Then, okay, then we have the values in the next time step. Okay, equations for solutions I will show you. Then we solve the pressure correction equation, and that's the like the most time consuming part of the algorithm, because this is a global equation. So basically, to solve pressure, you cannot do it locally. It's not like you go into the mesh grid and solve here. You have to solve the pressure equation in the whole domain at once. So that means you have to either solve the system of linear equations or use some kind of iterative procedure, like Gauss-Seidel or something like this. Yeah, and this is basically what I do here. And then if you do that, then you basically get the correction term for the pressure, and this correction term is then used to correct the pressure in the next time step. So let's see the algorithm from like above. Okay, how does this work? So we guess the values of velocities and pressures. We solve the 3 and 4. Then we solve the equation for pressure correction. This is the one which was there. Yeah, this one. This is the equation 6. After we solve that, we calculate new values of U and V. I will show you in a moment how to calculate them. So we basically use the pressure correction to calculate new velocity fields. We update the pressure and basically update the velocities. And then we again solve momentum and continue the loop. The simple algorithm is an algorithm for the steady flows. That means the time component is removed. And then that means we are assuming that it's independent of time at the very beginning of our calculations. We need to know the system that we are solving. And the variants of this are used in the top software, commercial softwares. One of the examples is Fluent, that is using simple C. The C is just an extension you can see in the literature more. Now, technically, how to really make this, because I showed you from the top, like how the algorithm works. Yeah, but to implement it, you need to know how to really make those, how to really solve that equation, how to solve this equation, so how to basically discretize them. Because you cannot do it in the continuous form, you need to go into the discrete world. And so that's pretty much about the numerical methods. But related to CFD, there are a little bit, maybe not different, because these are standard numerical methods, but the set of the methods used in CFD is very interesting. So first of all, we are using the so-called staggered grid. I don't know if you've seen staggered grid before, but it is used for in CFD very often. So the idea of staggered grid is that instead of discretizing your system in regular way for each of the fields that you have the same. So the standard discretization that you may first think of is that if you have three fields, the pressure, let's say the x component of velocity, y component of velocity. By the way, if you work with 3 dimensions flows, then people very often use just W as a third component, but we don't use. We have three fields, U, V, and P. And usually what you would think is to use the so-called collocated grid. So this is what is the first guess, that all the values are here, U, V, and P. Let's say this is I, J, and then this would be U, V, P of I plus 1, J. Something like this. And this would be the same U, V, P of, I just write like this, like these are three fields, of I, J minus 1. So in this way, this is called collocated grid. But using collocated grid gives you problems with stability of the discretized versions of numerical operators. Therefore, people invented this way of presenting the system in discretized world, which is called staggered grid, which is basically just that you move your grids in the space by half and keep the values of U, V, and P independently on the grid, such that the values of P are in the cross sections of the grid lines. The values of X components are just moved right by half of the spatial step, and the Y components are moved by half on in the Y direction. Okay, so that means basically that your Pij is here in the middle, but U is never in Ij, it's always in the I plus 0.5 or I minus 0.5. And so for people who are thinking in practically, it's always like, okay, so how to implement it? That's pretty much the problem, the only problem with staggered grid, because if you know how to implement it, then it's basically very useful, because then you have those values on half spatial step, and but with those values, all the numerical operators are written. So you basically use those directly from the grid. Then you don't have to interpolate or anything. That makes your life easier, believe me, if you implement it properly. Now, to implement it, you need to write down your own procedures. And the easiest way to do that, so I like the easy solutions, because the life is to make it easier, not harder, because you can write the special kind of structure with special kind of structure with what? With a special kind of structure in which you can get the values independently and so on. But what I suggest is to keep three fields, and that's it. So basically you keep U, V, and P independently, and then get from so you put the logic into the code. So you basically know which grid is moved and in which direction. So basically you have so now that's an implementation grid, That's two-dimensional grid in which you have three fields. So U, V, and P is the same, but you know that all of the values that are here are moved by half. All those values are moved by half, and all those values are basically in the right place. So if you want to have a 0.5, you need to know which index from the table is which one. I don't know if this sounds simple or not to you, because that's very hard to read from your minds. So you can basically give me some feedback on the paper, but I will move on. Okay, if you want to implement it and have problems, then I will let you know. But now have a look. all the okay. All the numerical discretized versions of our numerical operators, so partial differential operators, are now easily represented on in discretized version. So we basically have a first derivative in time, which is basically this. We have a second derivative in space, which is y plus 1. But you can see these are plus 1 minus 1 here. But this will be in a moment. You see, in a moment will be transferred. Then we have pressure in y and x. These are basically our numerical accuracies. Okay, so that's basically standard from numerical methods. I will not go now to discretize our equations. We are using those. Operators that we have here, yeah, and present equations 3 and 4, momentum equations, in discretized version on staggered grid. Because on staggered grid, we will be using operators which are basically, for instance, here, this is the difference is 2 times time step. And to make it second order accurate on a staggered grid, we need to use the proper distance. So now this is the form of the equation 3 and 4, okay, written such. Okay, I know that I could derive it, but it's maybe not a proper place to do that, because that's a way to write it such that you can implement easily, because then you basically compute those A, B, and just put into equation and calculate. Okay, that's a way to present such that it's easy to implement. Believe me or not, but this is very easy to implement, because you just need to calculate A, B, and put into this equation to calculate the new values of U in each of the grid, new values of V, okay? And where do we get A and B from? So we get from this equation where A1, B1, and these are basically defined here. Okay, that's a little bit of inverse way to present, because I could go from the main equation, discretize, and give you the evaluation such that you get those equations, because that's basically just an algebra, very simple algebra. But it's not necessary, because all these are given. All these you have on the right hand side are given on your grids. There is nothing that is not defined. Okay, and yeah. So what do we now have to do to calculate? So we have to calculate B4, B3, A4, A3, and so on. After calculating them from the grid, we basically get the capital A and capital B and put into the main equation. You see there is the time derivative. This time derivative, just to give you some intuition, this is this derivative. All the right-hand side terms are given in this equation. Okay, all the right-hand terms are there. Okay. Okay, so after calculating this 7 and 8, this is the first step of the algorithm. Okay, we calculate the new values of velocity fields. After that, we need to solve. Okay, there are the definitions of what is u dot, yeah, all these that are in these equations. I hope that you, as a people who program, just see the simplicity of this, because there is nothing like not given. Everything on the right-hand side is given. And okay, just this you will also need. Okay, then you need to solve Poisson equation. Poisson equation is the equation for the pressure, the one that linked the pressure and velocity. You remember, we have continuity equation, and if this is not fulfilled, then we need to solve Poisson equation on the whole grid in order to get the correction term. Now, this correction term, the Poisson equation is not that straightforward. I mean, it's not that simple as the equation for the velocity was For velocity, it was very simple. You go through the entire grid and calculate everything in each of the points, yeah? And that's pretty much it. For the Poisson equation, you need to make a iterative procedure. So we basically have we basically have to use the 4-point scheme for the Laplace operator. Laplace operator in the equation that we solve is this one. So we basically have to discretize this first, okay, on the left-hand side. And this discretization is given here. So we basically use the 4-point discretization for the Laplace operator, which is there. Okay, and okay, there are some coefficients. And on the right-hand side, we will have the this divergence term. Okay, this is the right-hand side of the equation, the divergence term. So there is the derivative of u component and derivative of y component in respect to y, and this is in respect to x. And again, d should be 0. So d basically, our goal is to have a d equal to 0. If this is 0, then we are basically done. But usually it's not after computing the first step, because for the new values of u, and we were making an error. And now you see the procedure. It's like this. Compute velocity, make error. Take error, compute pressure, compute the correction, compute the velocity again, and come back. And this back, this back. So one equation is keeping the other, and it's like a fight, okay, making an error in order to converge to the solution. And magically, it converges to solution. Why do I say magically? So study the subject. It's not like there is a mathematical proof it will give you the solution. It is like by it's by the simulation, by the experiment, by comparing to experimental results, to the theory. It gives a proper solution. It is reliable procedure because it's built on an idea that by doing an error, you put back the error into the solution by using force term, by using pressure. And then compare and again. But it's a numerical guess that this will be the solution. And it works. So people use it. Yeah. So that's the basically it. I will not go into revised. That's for you to study because we'll spend the whole lecture. This basically is the same for the time-dependent flows. So we have the so we have the changed a little bit the algorithm, the vorticity in a moment, but I want to show you the these are boundary conditions, and let me show you the okay, so that's basically it, because if you have the, I'm looking for the correction there. If you have the new pressure after, how to solve the pressure. So we basically do the iterations. So I use the discretized velocity and in the continuity equation, and the pressure discretized on a grid. We do iterations. Okay, there is a procedure. There is a iterative procedure in which we use equation 21 for all interior points on a grid. That means we are solving step by step this equation. Okay, and it's a it's called Gauss-Seidel procedure. So you basically iteratively go through the new pressure values, yeah, by using this discretized equation with the source term, and you get the new values of a pressure. The solution is also time independent because in the equation there is no time, and you end up after some time with the new values of pressure. Okay, I'm very sorry, but if you didn't have it on your numerical course, then it will need you to implement it or write or use some procedure from somewhere to solve, but it's a standard problem. The Poisson problem is very standard. And there are also other ways to solve Poisson equation. One of them is to build up the linear system of linear equations and solve it either probably also iteratively. Yeah, but here I use the very simple algorithm in which I basically repeat the same. Okay, and we finish when we have the new pressures. And then after having the new pressures, we basically go back here and calculate the U prime V prime, which is in Appendix 1. Let's go here. Where is the Appendix 1? Where is this? These are results. Okay, in Appendix 1, I put the corrections. So we have basically the correction term for velocity and x and y component, and a new values for the u and v calculated from the pressures, because these are basically the momentum equations for the pressure only. So as you see, what we do after, I'm sorry, I don't have the numbers of equations here. Okay, after calculating correction from the P, we need to basically solve the approximate momentum equation. So this is like a Navier-Stokes equation for the pressure only. So the correction step consists of calculating pressure and then updating the momentum, yeah, by using like simplified Navier-Stokes, because we'll get rid of all the other terms. We have the pressure force only. Okay, that was the reason for calculating the pressure correction was to basically update velocity by using these two equations, okay, and which are basically those, yeah. And then you get the discretized version, which is that, and that's pretty much it. So again, the procedure is, from the implementation point of view, now should be for you like not very simple, but maybe possible in your head, yeah, because you basically have everything. You can get momentum from very simple two equations that were at the beginning. Then you get the Poisson equation, you make the correction, and then go back into the solution of momentum. Poisson equation, correction, and so on. That's the simple method, okay? Semi-implicit method for pressure-linked equations. And the main paper for the simple method, first of all, this is the Anderson book, so the reference one, Anderson, Computational Fluid Dynamics, and then numerical study of viscous flow in cavity. This was using simple, and I think that's pretty much it. Those two will be the most standard. Okay, if you need, then I will give you some more. The results in a moment, but let's now move on into the so-called vorticity-stream function approach, because this is even simpler and it's more straightforward. This one? C? Yeah, zeta? Zeta, yes? Am I right? You know? Zeta, let's say zeta, okay? I'm not good at Greek, okay? Zeta? No, you don't know? Elizaveta, you should know. You are from the particle field. Yeah, this is zeta, yeah? Okay, so, right, so lucky me. Okay, so that's just a symbol. It could be A or B, yeah? The idea here is completely different. Now, let's close the simple, okay? Let's say you are prepared to read a book about it, and that's it. Now we move on into another numerical method in CFD, which is very interesting, because it was the simplest one for me, for instance, when I was a student, to understand and to implement, even though I was exposed to all these Greek letters that were new to me, because I didn't know what zeta is, and I didn't know what is the idea behind the vorticity and stream function. It was a new concept. But it was a time when I just was like understanding it, because it simplified things a lot. So let's say we now want to solve again numerically by using numerical operators, but in a different world. So we move from the pressure, velocity, into the world of a new fields. So we will not use velocity and pressure. We will use zeta and c. So we will use c and zeta functions, okay? And this is called vorticity-stream function approach. So we basically define vorticity, which is zeta, the vorticity. You can write down if you make notes, or just remember that we define a new field, the field of vorticity, which is basically the the product of nabla and velocity field, which basically in 2D is dv over dx minus du over dy, okay, in 2 dimensions. So now, if we define this vorticity in this way, because we are solving incompressible flow in 2 dimensions, it's pretty simple to calculate. Basically, if you have velocity field, you take the derivative in x and derivative in y, and that's it. Now, we also define a stream function, and these are only 2 definitions that we need to know. We define a stream function, which is basically deep c over dy equal to u and deep c over dx equal to minus v. And this c is obviously defined here, okay, like this. Now, why do we define it? Because if we do it, then we can combine those definitions with equation with the Navier-Stokes equation 3. Okay, let's come back into the equation 3. I'm showing you how to work with this basically document, because that's the pretty much what we need to do. So we take this equation 3, okay. Okay. And we write down the equation in a form in which we don't use separately x and y component, but we use the zeta definition, which was there. Okay, so if we take this and put into this equation, we will end up with with those 2 equations for x and y component, okay, which are now combined into one, and this basically will give us the equation which is more general, but it's not for u and v, it's for zeta, and we will get rid of the pressure field. So basically that will be an equation without the pressure component, okay. And yeah, and from those 3 equations we can derive the equation for psi. So basically the equation which is here, the equation for the psi function. Now, you need to believe me, this is like this, because I took it from the book, I didn't derive it. You need to, if you want to know whether this is true or not, you need to put the zeta here, and I was doing that, obviously, when I was doing the report. I have my notes somewhere, but I will not give you the, again, the regular, because we will spend an hour on deriving one of those equations, and this is not my point. My point is now, starting from those 2 equations, show you the simplicity of CFD solution here. Okay, that's a CFD course. We start with the Navier-Stokes equations written in the psi vorticity function, psi stream function. What is the name? Vorticity stream function approach. So we basically have Navier-Stokes equation in the vorticity stream function form. Okay, that's where we start. Starting from those 2 equations, okay, with these definitions of vorticity and stream functions, okay, you can easily derive Navier-Stokes from this. That's not hard, even for me, it wasn't. You can basically write down again the same form of in the same way you can write down the partial differential operators in discrete forms, okay, but then you can use non-staggered grid. That's the first simplification here. You basically, if you noticed what I told you just 5 minutes or 3 minutes ago, you now understand how easy it will be, because we don't have a pressure. Now we don't need to solve the pressure equation. See, we have a xi and psi. We are using those discretized versions of equations, which are basically, I will show you those, which are very simple. I will show you somewhere I have them. And then see how the procedure now is written. We are setting initial psi and xi. We solve the vorticity transport equation. Okay, in a moment I will show it. Should be somewhere in this document. Then we solve Poisson equation for psi, but we don't have a pressure. We obtain nu u and v, and we go back and we solve. We make the solution will be like this. Okay, that's a vorticity stream function approach. And from this, where is the equation? Why didn't I write it here? Where is the equation? Wow, okay. So I have them only in the code, not possible. But it was very, very simple. Okay. No, I didn't even write because it was, okay, I know why it is not in my document, because I was doing this just at the very end and I did it very quickly. It was very simple. The solution was much simpler because there is no pressure correction. We don't have the, again, we don't have the new, we don't need to correct the solution, because by definition it was rewritten in a way that by definition psi and xi have property of being the solution to incompressible flow. Okay, so let's finish here with this vorticity stream function. I just wanted to introduce you those two concepts, because you may be seeing them somewhere. And one can ask, so why don't we solve like three-dimensional flows, for instance? Because there is no definition of xi and psi in 3 dimensions. And that's the only problem. People don't use this approach in CFD. Otherwise, it would be used always. Okay, that's this. And now let's see the results, because okay, and the good news for all of you is that you don't need to use ChatGPT to implement it, because you may today do that, because all the codes are on my website. If you look properly, so simpler, and vorticity stream function is there. So all the informations that are not in the report are given in the code. I have a very simple C++ codes written in which are solving the problems, and these problems that those codes are solving are here. So we basically take the driven cavity, okay, and then we put some boundary conditions, basically the no slip condition for the velocity x and y, okay, on all this we discussed last week. So we basically put this. The more problem was with boundary conditions for vorticity stream functions, because on the boundary you need to basically put some kind of a solution, and it's not that straightforward when you don't use velocities and pressures, but you use psi and xi. But yeah, this you can also get from the definitions, and then you have a solution like this. And that was the solution I showed you at the slide. So basically, again, the flow flows on the from left to right. You have all the physical phenomena that happens. The here and there are the vortices, yeah, that appear. You have this deflection on the outlet because there is some kind of sucking here and there, and then the flow goes here. If you had more resolution, you would see the vortex that is created there as well, because there is no possibility that the flow is deflected without the vortex. It has to have some kind of vortices appear. And yeah, and then the way it is drawn is also a kind of special, because there is okay, there is no software that gives you exactly that. What I did was I put some markers. So from the marker and cell method, I knew that one can advect markers on top of velocity field, and these are markers, like hundreds of them, that are smearing out the velocity field. So basically, they draw on a velocity field. That's why it's a little bit darker here. It's not physical. The color is not physical. The way the visualization is done is such that you see the transport paths of particles. So for instance, this particle that is there, it's always going along the line like this. Yeah, so they are trapped, and they're basically, yeah, so this particle will go here. Yeah. Okay, so that's it. I didn't do a lot of things here that I could do, because I could change the geometry, I could put some obstacles and so on, but it was not the point of the report. The point was to create the proper solution, and this was the vorticity stream function solution that I was just checking what stream function is, what vorticity distribution function is, and so on. That there is a y and x component. I was playing with the solution a bit. There are the different ratios of cavities. So basically, if you have a cavity like this, but you enlarge it in y component, you can expect that this vortex will lose the momentum up to the point where the new vortex will be created. Yeah, and that's so yeah, one can play a lot with that. Okay, I also checked some convergence and so on. I was playing the convergence comparison of those three methods. And yeah, the Vorticity-Stream was the fastest one. Yeah, probably because of the way that we created the way that we because the Vorticity-Stream function has this assumption that the flow is incompressible, entangled into equation. There is no pressure, so that's probably why the solution is the fastest. Okay, and what you can do with simple and with those methods, basically everything in CFD, and that's pretty interesting because those methods are very robust. This is an example of a flow in which you have some y, the left wall has some velocity field applied as a boundary condition. There is some outlet velocity also assumed, and I just put the obstacles in the middle. That's actually the software that then I wrote afterwards, so that's why I will show you what is this in a moment. And if you calculate the flow, you will see all the results, which are basically, so this is like, I would say engineering, yeah? What we had here, that's very often, that's actually very interesting to say, this is physics, yeah? Because that's a physical phenomena in a single cell in which the flow flows with the top velocity moving and so on. And all this happens because the situation is the simplest possible. But here we are using it to create something more complex, and we have a flow over a tunnel with obstacles. So you see the main channel, yeah? And the funny thing is that was one of the first more complex scenarios that I was calculating. And now after some years, yeah, 15 or something, this actually is something that I'm working today even, because that's pretty much something like a porous medium through which the flow flows, okay, with some obstacles. But yeah, I do it in more complex way. But anyway, it was something like that. Now you see the x and y component of velocity. So you see the red is x and the y is green. These are basically driven cavities everywhere, but they are like changed a little bit. So those are phenomena that you observe. And this video of this is the most viewed video on my YouTube channel that I created some time ago. And has actually almost 40,000 of views. I don't know why people like it. I will show you in a moment. Okay, now this is the Vortex-Karman street, and it was calculated with the time-dependent version of simple, probably simpler. And the software that is using it is available on my website. So you can also download it and just play with that, because that was a time I was also trying to put my codes into the software. And yeah, you can basically draw the obstacles. We don't have time for that. If we have some time at the end, I will show you. But anyway, so that's it. And yeah, okay. Now it's a time for you to ask questions if you have. But I very honestly tell you that if I wanted to answer very detailed question, I would need to look into the literature as well, because I was working with simple long time ago. But now you see the main concept of the algorithm, and this is the most standard one. And I think I showed you it in the most simple way, so that you can basically go in and implement it. Yeah, there is no there are like whole books about simple, about finite volume methods, because this is basically this originates from finite volume methods, so you can study the theory and do it in a proper way. But then we would need to have a whole course, and I would need to give you the lectures from the book, which I want to omit here, because that's not the point. I want to give you the introduction to the whole CFD world. Okay, so that's pretty much it. Okay, that's those three. Now let's move on, because we are on the first slide, which is not good. Okay. Okay, and then 3 years later, and then I will just go very quickly through it, so that I won't give you much details, because that's one need to have the time to study it. Because what I did was I combined two concepts together, and I took my simple experience, the one I just told you about, the first solver that we had with this pressure correction and everything. And I took this simpler and I used marker cells. So basically the particles that are advected in the flow, in a moment I tell you something about it more, to combine them together and to create free surface solver. So what I wanted to do was the following. The idea was, so that was my master project. And what I did was I solved the UV equations. Then on the grid, on top of the grid, I had a distribution of particles, okay, that were advected with the velocity. What does it mean? So we basically take the derivative of of the x and y. So basically, let's say dx over dt is equal to u. That's we know, and the same for y. Yeah, dt equal to v, and we discretize it on the top of the velocity field that we have from the solution from Navier-Stokes. Then each of these particles can be moved in the space. We assume particle has a zero mass. So it's a neutrino, yes? Anyway, so we have neutrinos I can put into my... anyway, so we have a particle that has zero mass. It's advected with the flow, so that means it will always follow the flow field. It's exactly the same I did in the driven cavity. The particles that were smearing out in the visualization were massless particles, because I just used them to draw like this many times with some opacity, and then I got nice picture. Here was different. I used those particles to mimic the free surface flows, because in cup of the coffee cup, yeah, in the coffee or in the glass, the water has some surface. It has some volume, but it's not everywhere. I mean, the fluid is everywhere because air is a fluid, but there is the rapid density change. There is a water and there is a air, okay? And I wanted to simulate it. I was interested in free surface flows. One day I will come back to this subject probably, but not now. I have other ideas. But anyway, the idea was I want to calculate droplets in water. I want to have a breaking dam and everything that flows like river or something. So those particles were used to mimic the movement of the free surface. And I used some very simple boundary conditions on the border of the fluid, non-fluid part. So basically, I was solving the equations only in those parts of the domain where the particles are presented, yeah, are existing. Okay, so the idea was to use the very similar algorithm to the marker and cell, you remember from the very first lecture, but to use the simple algorithm to solve for Navier-Stokes. Not because marker and cell used very direct way to solve the Navier-Stokes. Here I wanted to use the simple. Why did I want to do that? Because I wanted to improve results and get the proper splash of liquid drop, because it didn't work for me with the original approach. So I used the non-collocated grid. So that means staggered grid. Sorry, this is wrong. It should be staggered here, because I used staggered grid, not collocated. Yeah, I used the free surface approach. So we had an empty cells, surface cells, and the fluid cells, similar like for the similar like for MAC. And I will just show you a little bit from my thesis, so that you see that those parts that we just discussed are here. Unfortunately, it's in Polish, but today isn't the problem, I think. If one wants to study, then yeah. Okay. Let's just open it. Okay, it will open in a moment. Okay, and yeah, now we are solving the time-dependent equation. We have the solver is explicit again, so we know the time evolution. So step by step, we know the new time, and the markers are representing fluids, so they can be also used for visualization. So I use those markers and I directly draw them on the. I don't use them only to define where the fluid is existing, but also to make the visualization. So that's how it looks like. This is a breaking down problem. That's from my exactly from the thesis. These are results. So we basically have the initial problem is like this. You have a part of the water like that. So there is a column, and this splashes to right. This is already some later times, and this is compared to experiment. And this is exactly how the people in CFD are comparing the results of numerical codes into the experimental results, because there is no other way to validate the CFD codes, because they are very complicated. There are no like analytical solutions for problems of splashing droplets or something. Yeah, that's a very complex. So you need to have an experiment and compare. And you see many phenomena that are existing in an experiment are existing here. So you have vortices here and there. You have like this bump of water on the left wall. It's available here. So you see the solution is there. And now, of course, it can be compared in a proper way, like with some plots and so on. This is what people do. Yeah. And I obviously didn't have this experimental results, but yeah. I also did splashing because I wanted to do splashes of droplets at those times. And I did the splash of droplet on a flat surface. These are results. Now you can compare to David Potter, yeah, book, because that's pretty much what I wanted to achieve. And the splash of liquid drop. And believe me, I don't know if you had a project like this before in your life, but I spent I don't know how many. It was so frustrating because the splash of liquid drop in deep pool did not work as I wanted. I never had and I didn't know the methodology of scientific work at the time. I was doing this like hitting with head in the wall. I was trying to get exactly what those people got in the book. And I got crazy that it didn't work because I was so sure that from many sides the solution was proper, but I didn't know that it's the wrong way. I should have found some kind of an experiment and compare the main physical phenomena to what people in experiment get. And at those times, I didn't have support to do that in a proper way. Therefore, I was trying again and again doing the same. So repeating today I would do it different, and I will do one day this proper splash of liquid drop. And let's wait. So again, but I got nice results. Okay, especially the initial part of the droplet splash was just perfect, because what I got was the creation of the corona. This is a corona that creates on the borders of a splashing droplet. In 3D, you know, because of the surface tension, you have those little droplets that are spread around. This is very famous photos that people do, that the droplet of a milk going into deep milk pool gives you the corona around from the little droplets. So this very much what we see here, but here it's two-dimensional, therefore it's not like a corona of splashing, but it's like created there is a pressure that pull out the water in a way that this special kind of shape is created. Now, this is a moment where the fluid is compressed. I mean, there is no compressibility, obviously, but we basically push the flow into the to create the crater like this, okay, the hole. And because of that, there is a pressure upwards that wants to pull the water back into the y direction. The pressure comes from the static pressure here. Yeah, so you have a pressure that wants to pull it back here, and you have this very nice jet that goes upwards. And the problem I got was, and I never forget it because I never got it, was to make the detachment of the droplet on the top. And I didn't get it. I was like, why this droplet does not go out? that was so crazy because people got it in many situations, in many experiments. It's like physical phenomena that I didn't catch with my code. And I was trying to get it. Now, today I know that most probably I didn't have the model for surface tension, because if you have a high pressure here, and this pressure wants to push the flow upwards, because of the pretty high velocity of this top part, probably here this surface tension would create a force that will make it even stronger to go up. The problem was I didn't have a model for surface tension, and believe me or not, but the author of the original Marker and Cell report, Harlow, that was a guy from Los Alamos, I contacted this professor. I wrote to him that I have a results and it didn't work. And he replied me. He was like 70, I don't know, he probably, I don't know if he died or not. It was at the time, he was a very, very old guy. And I have this email. He answered me and he wrote me to consider the surface tension and so on. And, maybe I find it and show you. That's pretty interesting, because I was like, not very experienced, and I didn't know whether I can write to him or not. It was like, I will write and just tell him it does not work. Yeah, and he replied, that's very interesting. Harlow, that was a guy. Okay, but anyway, there is a video I will show you, because that's one of the best ones that I got. These splashes, I have hundreds created at the time, but one of them was used for my master presentation. That's pretty much this. So you basically have a splash of liquid drop, and yeah, again and again and again. We can watch it. Yeah, so you have this, that's the best one I got, yeah, I was tuning parameters of the flow and so on, but you see this almost went up and almost was detached. And the best is that I even today believe that with a proper properties, might be that without this surface tension should be possible. You see, again, I say the same. The student was saying the same, because when I put the surface tension, that's pretty much obvious it will happen. But in the book they showed without it, they had the same result. They didn't have surface tension in the original Mac code. And unfortunately, this professor did not confirm me whether the surface tension was or was not used. So that's actually a kind of research question, whether this surface tension is or is not necessary to create the detachment of droplet. Maybe I write grant for that. You see, that's something one can study for years, because we don't know. Okay, and now I will show you a little bit more about what results I got with the code, because that's actually showing also something about the way one can develop and work, because I created very nice code that had a lot of other capabilities. And the best I achieved was not the splash of liquid drop. The best was this one, and I really love it. Oi. Because that's showing the properties of the code. That shows you what I can achieve with that. All the splashes, all the vortices and so on. I can basically, that's the only one. I just put some initial flow here, and I get all that. I get the cavity, I get all the physical phenomena in the tank of liquid water. I can now simulate with the code, because you can do basically whatever you like. You can pour the water from what side you like. You can make a bottle, you can make a hole in the bottle, you can put the pressure, you can put here and there. That's all, all this. You see, there is a vortex, this is cavity even, but it's still with the free surface. Okay, it's the most developed CFD code I ever created. Now I work with much simpler stuff, because one has to do PhD and so on and so on. So, but this still is in my heart and mind, because it's really very nice to make the free surface flows with yeah. Anyway, so then this is a vortex karma street. This probably spent the most time to make this picture for my master, because I like pictures. I'm very much visual guy, and I wanted to make a nice figure for the very standard phenomena in the flow, which is the vortex Kármán. Vortex Kármán is a phenomena that happens in the channel. So basically, you have the some kind of an inflow here. So you have a boundary conditions, that's the condition that tells you that fluid flows from the left to right hand side. You have a tunnel, so this is like a wind tunnel. You have an obstacle. Here is a part, half of the circle, so it's like a disk. It's still two-dimensional, but the method is three-dimensional by principle. You can basically put another equation, no problem. You can make it 3D, and you push the flow. The flow is everywhere. But now it's like in experiment. In experimental work, what people do, they have a wind tunnel and they put a little ink or oil into the water so that they can see where the particles of the ink are flowing. So the fluid is everywhere. So it's not free surface. It's like fluid is everywhere. The fluid is the same everywhere. But we put some particles here, 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 here. It's like a stream of particles continuous so that we see where the fluid is flowing. And what you will observe is a special kind of structure that is time dependent. So the structure is moving right. So all those vortices are just moving. It's like an onset of turbulence. Okay, it's like a moment before the turbulent effect would appear, because this is time dependent and all this moves right. And basically it's a called vortex Kármán street. And you can observe it in the natural phenomena as well. Yeah.
Because
yeah. It's you can see many movies and experiments where the vortex Kármán street is vortex Kármán. There is some kind of this or that, I don't know, but there is some accent on Kármán. Anyway, so yeah, this is and this is only a snapshot of the movie. The movie I will show you because I have it somewhere on my YouTube. So in a moment we will show it. Okay, and that's from from my master. At the very end, I just put it as a last page. I'm sorry, I have to drink water. Yeah. So it's okay. And the colors are not for the fun. I mean, they are for fun and for our eyes, but they are showing the velocity field. So there is a y and x component, yeah. And particles are showing the shape. They are called, by the way, these are not streamlines, okay? If you want to call them properly, they are streak lines. There are two ways of calling the streamlines and streak lines, because streamlines, these were in the cavity, the lines of a steady state solution, okay? If you read the books or literature, streak lines, streak. Sorry for giving definitions because they are boring, but I know, but anyway, it's worth to know. Streak lines will be particle paths in the time-dependent flows. Okay, this is what we observe here. Okay, let's move on. You can, and today, okay, today I'm working with these systems. And the very short story about it, so that you maybe, if you plan your work or your career in academia and so on, you will be interested how the people develop the ideas. So the idea was that I was a CFD guy without any support here, because there was no one working with CFD, and I wanted, okay, we decided I will do PhD. And then my professor, Koza, with whom I started to work, was more like a statistical guy. He was working with statistical physics. And then we combined this together. That was actually his idea. He said, I like statistics, you like fluids. Why don't we do porous media? Because that's very much about statistical work with the averaging and so on. There is a lot of statistical physics input into the research that we are doing now. So I'm working with systems like this. These are systems in which, so if you have this vortex Kármán, imagine you have more obstacles, more those disks everywhere. And then if you have more of them, then the flow through this will be much more complex. So the fluid will go into different narrow channels. There are a lot of physical phenomena that happens. For instance, if you put a pressure difference in a porous medium, there will be an emergence of flow paths. So there will be like channeling effect. And this channeling effect is not obvious because we don't know where the fluid will flow before we solve the solution. We solve the equations. So the solution gives you the information where the channels of flows are. And that's pretty much what we are studying. So, and then I use many different concepts like the tortuosity, the pi number, the inertia effects. Now, today I have a grant on calculating inertial effects in the porous medium. So basically I push the flow towards limits of velocity. So I really increase the velocity up to the point where nonlinear effects are created. Yeah. And that's pretty much the systems that we are calculating. Okay. And we are solving Navier-Stokes again and again. Yes. Sure, this one.
Is it that like the green color represents that the strength of the field is stronger? Or?
Yes. So the more intense green color is, the more y value of velocity is, the velocity y component is higher. The more strength the red color is, the larger x component of the velocity is. Therefore, if we move into the wall, there is a wall, there is a like black color because the velocity is zero here. Both y and x component is zero. Then if you move into the middle, the intensities will be higher. Yeah? And then this green color is not constant. It's moving into x direction. This is the convection term I told you. Yeah. So the momentum is moved with the flow. The fluid is moving the momentum with itself. This is the convective term in the Navier-Stokes equation. Yeah. That's how you can understand it, that the momentum is moved with the mass transport. Okay. Good. This is flow. Yeah, the activity I will continue because I have more about it. I want to tell you something. If you got interested in CFD, then there is a workshop that we are organizing each year. And this is actually something I'm very proud of because we already have the 11th edition was last year. No, it was this year, 2024. I always organize with different people. Now I have a group around grants, so we are doing this together. So it happens here in this institute in the Rzewuski Hall always. We always have it rented for Friday. And many people from around, even from the world, are coming because I already know some people that like to come here to Wrocław. You know, 11th edition is already like a community of people that like to come for this workshop. So you are all welcome because it's always open. There is no fee. We always laugh that at my workshop there is no fee nor coffee because I never prepare coffee because I hate to prepare it for the conferences. So then I don't want to engage my students to do that. We just don't do this. There is a machine, one wants to have it, then he buys it, and we don't have a fee. So the people come very likely because they don't have to pay anything and we don't have this administrative burden. Yeah? We don't have to do anything. I just call the people and they come, and that's perfect conference, really fantastic. So everyone is welcome. Yeah. And then each year the different people do the posters. Come on, this was me, terrible. This was me, terrible. Me, that was my student, different. That was me. That was me, but then was my PhD student, my postdoc, and my PhD student. Come on, this is beautiful. That was done in, these are streamlines of flow through one of the systems of David Strzelczyk. He just submitted thesis, so hopefully will be defended in 2 or 3 months. And then rendered it in Blender. That's, you know, artistic work. I'm sorry? You mean colors? No, the colors are artistic, but the shape of the lines is the fluid flow through the system of packed grains. So he had like 3 grains that are in the simple cubic cell, like repeated. He was doing this for research, and then took his velocity fields and created those lines and imported into Blender, and then put some artistic vision. And this, for instance, is interesting because this is a result of a flow, similar to one that you were asking for, so the one with the vortex-Karman street, but it is a high Reynolds number. It's like thousands. I don't remember exactly the Reynolds number here, but this is a result from Sakhrij, from our postdoc, the girl that was here very long. Now she is working on the visa problem, but then she comes back because she's still with us. And she is the specialist in calculating turbulent flows, and this is pretty much turbulent. So now you see all those little stuff that happens here is a turbulence. It's very hard project that she is conducting. It's calculated on our WCSS center in Polytechnica. And believe me, they wrote us an email whether we know what we calculate, because this takes so much resources. But yeah, that's actually turbulence, and that's very hard to calculate. And that's a poster from Sakhrij. And this is Odra River, by the way. That was an idea from David to make an Odra flow. Yeah? Much better than mine. Yeah. But I will do the droplet, and the last one will be with splashing droplet. Yeah. Okay. Oh, that was an idea that came up here. Yeah. That's more about the course, but yeah, again, what we are doing now here is 10 hours of lectures, CFD. My idea is that you get interested in CFD, because this for 10 hours is enough if I get you interested. I want to give you a chance to implement your fluid solver, so you will do it, and also use the software. So you have 2 sides, okay, of doing that. And I also want to introduce you to the subject of my grant. This will be a little bit at the very end, and I looking for students, of course. So I'm very open for the projects, but it's up to you, and I don't force anyone. There is nothing like you need to, yeah. Now, this is not for this course because I'm still in the contact with director. How do we evaluate this course? But don't worry, we'll do it in a way that you will be, as I told you, you will be given 2 exercises with probably a little report where you put everything and just write down what you see as an exam. We'll not do an exam on the paper. That's not necessary on this course. I want to make it practical. There are different solvers and so on. Yeah, this is FHP. This is lattice gas automata. And I will also tell you something about it, because the lattice gas automata gives you the introduction to lattice Boltzmann. And this is what we will be doing next week. And that's amazing, because FHP is did you hear about FHP before? It's like it's a very simple cellular automata model. Cellular automata, because it was a time when Wolfram, yeah, you know Wolfram, has written a book about cellular automata, and it was a time in physics where people believed that cellular automata will solve every partial differential equation. It didn't happen because of some problems, but the idea of FHP, I will now draw it in on a different in a different grid than the usual FHP works, but just to make it simple. Imagine you have a model in which you have particles. Okay, let's simplify the physics up to the limits. The very idea is that you have particles on a grid and they move in some directions. And let's limit the directions only to y and x component for the moment, okay? Now, those particles can move. So the one step of the algorithm of the model of cellular automata is that all the particles are moving in the direction of velocity they have, because they carry the information about the direction. So in the next step, the situation is like this. This moved here, and this has the same velocity. This moved here. Let's draw one of the particles which like this, okay? Now, this moved here, so change 1, 2, 3. Okay, this one moved here, so this moved from here there, and it carries the momentum. This moved here, so it will be there. And now the problem is here. Yeah, what happens? Okay, let's simplify. I will not solve it now. Here, let's do it this way. Now, the problem is there. What happens? Now, we need to solve the collision problem. That's the second step. The collision means the velocity will change, because what happens with in the collision in physics? When you have two particles, they collide. Yeah, I mean the particles not in a way like the particle physics says. We say about the standard like the pool balls, yeah, or whatever, like classical particles. They hit and they change momentum, so they can basically hit towards themselves, then the momentum will be reflected. But they can be like that, and then the momentum will be just rotated, yeah, by some. So then there are many ways one can solve collisions. In this particular model, the collision solution is very simple, because we basically say that whenever they go like that, they will be having velocities like this. Yeah, if they go towards themselves, then we will rotate by 90 degrees, and that's it. That's a model, okay? Don't even go into the proper how this is close to the reality. That does not matter at the moment, because it's statistics. Now, imagine or not, but this simple model. So then in the next step, that means after collision step, they will rotate here and there, yeah? So they will move and rotate the velocities. They will be in the same spot, but with the velocities like this, because they collided. And okay, now I may be not very strict into the rules of the concrete version of the cellular automata, because they may be different. This cellular automata is called HPP, from the names of the people, Haslacher, Pomont, and the third one I forgot. Okay, this is PRL paper, and the best is that those simple models represent solution of Navier-Stokes. And you can basically, from FHP, the model like this, a little bit more complex grid underlying here. If you do it on the triangular grid, yeah, with the more directions of velocities, if the directions are not only 4, because this is the simplest one, this will give you gas, okay? HPP gives you the gas. But if you go into this triangular grid, okay, like this, and so on, okay, into triangular grids with more velocity directions, then you get so-called FHP, Frisch-Haslacher-Pomont. Okay, these are the names of people who published a paper in Physical Regulators, I will show you next week, in which they show that solution to this cellular automata gives you solution to Navier-Stokes. And the proof is not here, because that was solved with Lattice-Boltzmann, but the proof is probably here, I remember, because that was done with the FHP, I guess. But I have solutions with FHP as well, because I had a student who made a bachelor science thesis in which she solved, that was a girl, she solved Navier-Stokes using this simple particle models. It's amazing that you can go in this way. And what Ludwig Boltzmann did was he averaged those particles. So he basically created so-called the statistical theory to solve the same by using Boltzmann transport equation. So basically, Boltzmann has created a statistical picture for this particle phenomena. And this is what is the origin of the Lattice-Boltzmann method. I will show you, yeah? We'll go from the cellular automata into the Lattice-Boltzmann method, okay? We still have 3 minutes. That's an solution of Lattice-Boltzmann from Beata Kowal, our employee now. She is now not working with CFD, but she made a wonderful implementation, and she got the proper vortex Karman street, of course. Yeah, we also had solutions to high Reynolds number flows cavities. This cavity is much higher Reynolds number than we had in my solution, you remember, because you, for instance, have this vortex here, or the vortices here are doubled. So you basically get 1, 2, and third vortex here. You can even go higher, of course, but the solution here was not simple. Yeah, there was time that at this particular course I was giving students the task to make the driven cavity as at the highest Reynolds number possible, but it didn't work in the way I wanted because people were not able to really go higher and higher with some, I mean, people did not have the experience. It needs to have some experience, but this is one of the challenges that are in the in this community. If you have some solvers, yeah, because these are the solvers that you can implement after this course. So simple, you know, FHP you will know, and LBM and LBM Tau1 I will give you next week. So these are basically solvers that you can use. You can also use OpenFOAM and basically go higher and higher with velocities. So for instance, here, the vortex Karman Street that we had on the figure that I showed you, I didn't tell you about the Reynolds number, but the Reynolds number was about 150. If you increase Reynolds number up to 30, 300, you get it a little bit different, but still you see those vortices that are just traveling. But if you go over 1,000, like 2,000 or something, you get those vortices to create little vortices. And this is already an onset of turbulence. Around 270,000, there is like a turbulent flow. You cannot even understand what is happening here. People from turbulent community say they don't know what turbulence is because this is like everywhere. I mean, statistically it is measured, but it's not simple to, yeah. And then, okay, I like to do it very often at the very end. I will just show you one of the things that we will be working with later. And this is the LBM Tau1 paper. This is Lattice-Boltzmann method, the simplest possible variant, Tau1, which will be given to you. It's a paper from 2021. I written with a guy from University of Warsaw, and it's a simplified solver that I will ask you to implement. And this will be your task. Therefore, I want to mention today so that you already know what we will be studying. But don't worry if you don't get anything now, but I will show you, as I always like, the simplicity of the task that I want to give you, because the paper, after the whole theory and the whole, it consists of short numerical code. And this short numerical code, believe me or not, is solving driven cavity. So if you copy paste to your C++ compiler, you will basically get driven cavity velocity field. And your task will be to copy it or rewrite, understand it, get the velocity field, draw it, compare to the literature result, make a report. Then you will be given a software, the ready software, that you will be doing the same. And then you have to compare this to the software results. And that's pretty much it for this course, okay, from the practical point of view. But I will give you the lecture next week so that you understand what is happening here, because you basically need to do that. Otherwise, it's a pointless, because it's not only about copying. But today, with the old GPT stuff and everything, I don't expect you to implement from the scratch. I expect you to understand what is there and to work with that, okay? And this will be your task. Thank you very much. That's it. We finished the lecture. And see you next week.